Along with the idea of vibrations and simple harmonic motion comes the idea of waves. And there are two different types of waves that we're going to be talking about. Those would be transverse waves, or the second one is longitudinal waves. So a transverse wave is defined as something that... Actually, let me go back for a second, and let me actually say what you need in order for a wave to happen. In order for a wave to actually exist, what we're talking about some disturbance through some medium that gets propagated along. And so in order for that to happen, you need some source of disturbance, number one, and you need some medium to travel through, number two, and then number three, you need some connection, whether it be some physical connection or mechanism, to have a segment of your medium communicate with another segment of your medium. So the slinky, for example, I can make this move because it's physically connected. And so we can talk about stuff on strings, we can talk about pulses, you can talk about sound waves, because the air molecules can bump into each other. Those are all ways to actually connect the different parts of your medium to make a wave propagate. So with regard to propagation, meaning how that wave is moving through your medium, there are two different ways. One is transverse, and the other one is longitudinal. And the transverse says that the motion of the wave is perpendicular to the displacement of the medium. So for something like this slinky, I'm sending a wave down, and it's moving up and down. It's not moving back and forth. The displacement of this is moving up and down, but the wave itself is traveling this way. So your typical transverse wave looks something like this, where it would be, if you had some string attached to the wall, it would just be some straight line. And then you disturb part of it, you give it some energy here, and this little bit will end up moving itself down the line. Okay? That would be the transverse wave. The displacement moves up and down, but the wave itself moves across. The longitudinal wave, on the other hand, that would be, for example, sending a pulse across the slinky, where you end up with a section that is more compressed and that travels down. So you actually do have the wave actually moving in the same direction as your displacement. Okay, not perpendicular, but in the same direction as. And that actually is how sound waves get propagated, and we'll talk more about that in the next chapter. But you end up with, say, a spring that is more compressed here, you have the lesser part of it that's more stretched out here, and then that compressed region will travel down the spring as the wave actually moves down. Okay, so this compression will travel down, leaving regions of rarefaction, which are regions that are more spread out. But those are going to be two differences between these types of waves. And we're going to talk a bit more in general about the transverse waves, because they're a bit easier to talk about in this context. So, just like simple harmonic motion, which these waves are exerting, if they're going to be periodic in this fashion, they are going to have an amplitude, and a frequency, and a period, and also a wavelength, which we'll be able to talk about. So the amplitude would be the maximum displacement from equilibrium. So if there were no wave going through this string, for example, then it would be just straight across. Otherwise, then the amplitude, I mean, as the wave goes, it goes up to a maximum point, and then goes down to that minimum point, and that would be the amplitude of your wave. If you are measuring between identical portions of the wave, whether it be between two crests, or two troughs, or two identical other places, that's going to be your wavelength, which we call lambda. Okay, so that's going to be a distance. It's going to be a measurement in terms of meters, centimeters, etc. Okay, that's going to be your distance. The period would be the time for one full cycle of the wave to pass by. Okay, so the time until the wave starts repeating itself, that's the time for a period. The frequency is the number of peaks that pass by in a given time, and that would be 1 over the period, just like we had for the idea of simple harmonic motion. So F equals 1 over t. Now, if we're talking about the speed of the wave as it's traveling down here, that's going to be related by the wavelength times the frequency. You can think of it as it's the distance the wave covers in a certain period of time, or the distance for one cycle over the time for one cycle. And that would give us that relationship of the speed, but of course 1 over the period is the frequency, and so these two things are completely equal. Okay? So that's the basic idea for what happens with the wave, just for its general nature. And we can talk about what happens when a wave comes in contact with a fixed end. So if you have a string and it's attached to a wall, it's not going to move, then as the wave actually propagates down, let's say I send it out this way, and it's approaching it, okay, it's exerting an upward force on the rest of the string. And so it's going to want to exert an upward force on the wall, but the wall isn't going to move because it's much more massive compared to the actual string. So what happens is Newton's third law tells us that the force from the wall on the string will be pushing down. And so in this situation, the upward pulse will be reflected back downward, and it will travel back this way. If instead this end were free to move, that wouldn't be the case. It would be reflected back in the same regular way as the way it hit. So it would come out this way, and it would go back the same way. But if it is fixed at the end, it would come back, and then it would go the other way on its return journey. If you have two waves that end up interacting with each other, or encountering each other, they will interfere. And interference usually has a connotation in our society of being a destructive thing, but you actually can have constructive interference or destructive interference. So constructive interference would be where two waves actually add together to amplify each other, and destructive interference would be waves that come together to cancel each other either wholly out or partly out. So let's say, for example, that we have this wave propagating this way, and then someone on this side of the rope decided to give that much of a wave that's traveling down this way. Okay. They travel along. At the very center where these two things are going to actually be in the same part of the rope, they actually will add together so that you get an amplitude that is the sum of both of them. And then right after that, this one will keep going left, that one will keep going right, and it will just look like they just passed through each other, because they did. So you'll have the bigger one over here, and the smaller one going that way, going on their merry ways, separating out. Okay, that's constructive interference, where they amplified each other, just simply adding together. We call it the superposition principle. You can add those two things together. Okay, and then the waves will just pass by unaltered. If instead this person over here that's holding that end of the rope decided to put a wave in the other direction, then this would still move that way, this one moving the other way. When they came to the center, let's say this one was a little bit bigger still, then when they came to the center, because this one's somewhat bigger than this one, you're going to end up with a net below, so you're going to have a slight blip there, and then they will continue on their merry way, the way they were going. Okay. If these two things were exactly equal, this center part would be 0. But the wave would still show up once they passed that center point. Okay. So that would be destructive interference, because they're able to cancel part of each other out. Okay. And the superposition principle, like I said, allows us to actually add one to the other, because they're both there. they both contribute, and they contribute in a linear way. So we can just add them together. So we add, in the previous example, we added the positive amplitudes. Now we have a positive amplitude and a negative amplitude. Okay. More stuff talking about speed of the wave on the string that we talked about at the end of class was that you do have to think about the properties of the actual string itself, because the speeds of the wave traveling down the string will depend on what it is made of. Like, say it's made out of a slinky, say it's made out of electrical cord, or it's made out of some big heavy nylon rope, or some other big rope you might find attached to a boat. The different properties of that material will actually affect the speed. And we mentioned in class that this is the behavior, that the speed is determined by the tension that the rope is under. So if you have the rope and it's a little bit slack, okay, then the rope isn't actually going to be able to, the rope has lots of freedom to move, okay, but the resulting speed of the waves as they pass by is going to be slower than if the rope were taut, or the rope has less freedom to move, and so therefore the waves, the amplitude is smaller, and the waves can travel more quickly down the rope. So the greater the tension the rope is under, the faster the wave is actually moving. Now, down here, this is what we call the mass per unit length. Okay, or some people call it the length density. Okay, as opposed to the volume density. And now we're just talking about one dimension. We're talking about the mass just along the length. And so you can think about different materials that are denser for a certain length than other materials, and that's where they would have a different mass per unit length. The ropes that are denser take more energy to actually make it move. Ropes that are lighter, they're more easily moved. Okay, and so the ones that are more easily moved, you could generate a faster speed more easily. So there's an inverse relationship between the mass per unit length and the speed. The greater the mass per unit length, the denser the rope, the slower the wave is going to travel, because it's harder for it to actually move through the rope. Now, if the rope is less dense, then you're able to actually get a greater speed. So it has a direct relationship, of course, with the square root involved, with the tension, and an indirect relationship with the mass per unit length.